Welcome. In this one, let's take a look at interpreting partial derivatives visually and finding them. You'll see it's kind of an interesting experience. Imagine that we have something like a simple, humble rectangle. That's all we really need to get at the essence of it. Let me just label some sides here. So specifically, imagine that this is now x, this is y. So based on this, here's a question you can ask. What happens? How does the area change when, for example, x increases by 1 unit? So what I mean is, imagine that x grows 1 this way along the horizontal, which means that the total change in the area is all of this. This is how much the area changes by. Let's shade that in so we can focus on it a little bit. So this is the change in the area. What is that value? Well, we can quantify it. Say that x has changed by 1 unit, so this is your x right here, 1 unit. The vertical dimension, since it is just a rectangle that has appeared to the side of the original rectangle, the area here will be equal to 1 times the vertical dimension, which is y, which is then just gonna give you y in the first place. So the area that has appeared, the change in the area that is equal to just the value of y, which is the height of the rectangle. For example, if y has the value 2, then the extra area is 2. If y has the value 10, then the extra value area is 10, you see? Let's also confirm this in a slightly more mathematical way, because it's kind of fun and interesting to do. So imagine that now I'm going to do this mathematically, to be more rigorous. I will say the limit as delta x here approaches 0 of x plus delta x times y minus xy divided by delta x. Where am I getting this? Well, this simply says the following. Let's focus on it a little bit. This is present because x plus delta x, this represents the original value of x increased by delta x. So in our case, that would be roughly like saying back in the rectangle that it corresponds to the original x here. But instead of writing 1 in that position, imagine we just write delta x. It's how much we're increasing the x by. Then you have y, so we're multiplying x plus delta x by y because this top piece right here, this then forms the area. So this, in terms of a picture, would be as if you were doing this single piece. This is the area that corresponds to this. This is your x, this is your delta x, and this is the y. So that total area is all of that. That's this expression right here. Let me zoom in on it with the color, this. Then we're going to subtract away xy. So what is that piece? Well, that piece is simply equal to this original area, if you like, which is just the x multiplied by the y. So that's this piece without that extra strip on the side. That takes care of that here. Let me do this one a different color. And lastly, at the end, you divide this by delta x because that means that this quantity right here, the delta x, shrinks over to 0. And you're taking a limit. That's why you need to let delta x go to 0. It's basically as if you were looking at what happens when this extra strip on the side has a base that approaches 0. Basically, it vanishes. So here, let's actually carry out the work. Now that we've motivated it, I'm going to have the following. I need to take this y over here, and I need to distribute it over to the x and over to the delta x individually. So I'm going to have the limit as delta x approaches 0 of distribute, and then distribute again. So xy plus delta xy minus xy divided by delta x. Let's work that out. So when I look through this, I see that, for example, like this one will cancel with this one because they're opposite signs. So the limit as delta x approaches 0, what's left over then is delta xy divided by delta x. And then lastly, you see that this cancels with this one. And all that remains at the very end is basically y. But think about this y. We already have this y. We found that same y up here. Right, this is my y. And this is the same as the y over here. This second y, so to speak, on the bottom of the page, we find through a pretty elaborate mathematical argument. The first y up here we found through simple geometric reasoning, and they're the same. That's kind of interesting. I want to repeat this one more time, but in the other dimension. So I'm going to skip some of the detail because it's essentially the same thing. But take a look. Let me turn my grid back on so I can make a good looking picture. Draw the rectangle in here. So imagine that again, we have a rectangle like this one, and here call this x, call this y, and what we're going to do is grow our rectangle in this dimension. So y has increased by 1, which means that the change in the area corresponds to that extra rectangle that has appeared across the top. So in other words, this is the new extra area, but the value of that area would be equal to the following. So say that this is an increase of 1 along the y-axis because you've gone up this way, and because on the bottom it's x, that means this is also x, which means that the area, the extra area that has appeared, is equal to x times 1, because it's the bottom times the height, which is 1, which is equal to just x in the first place. Let's now express this mathematically. So again, remember that the area A of the shape is equal to x times y. So if I put this down over here, A equals xy, then if I differentiate with respect to y, and why should I differentiate with respect to y? Remember what that means. That is so because y represents the vertical dimension, and our shape is growing in the vertical dimensions, going up. It's extending its height, which is y. So for that reason over here, I'm going to differentiate with respect to y. I'm going to get dA dy, and this is simply equal to x. I did this one using a simple rule that perhaps you've seen before, the power rule. So in this context, remember, you basically differentiate the y away, and you treat the x like a constant. That is so because it's telling us that this value of x is the same as that value of x in that position. They mean the same thing. It's kind of really interesting and fascinating how all of this stuff snaps together into a beautiful comprehensive whole. This is all of our work. Thanks so much for watching.